So in this video, I'm going to continue where we left off in Friday's class. With the snow, obviously we weren't going to be having in-person class, which was kind of expected last week. Sorry, I get really tired when it's snowy outside. I don't know if other people are affected, but anyways, so I'm just recording this video. I was given the option to have an online class, and instead I'm just gonna record a video for you all to watch instead of having like some Zoom meeting or something like that. So we're just gonna continue where we left off. I haven't graded the quizzes yet, but I'll have those graded by Friday of this week and passed back to you. And there should be another quiz this Friday. So kind of entering their routine here. And I guess the only other piece of news is that I pushed back the homework assignment due date. So that way it was going to be due tomorrow at 11:59 p.m. instead of tonight at 11:59. I've seen some people have been submitting it online. So it's a valid way of turning it in, or you can turn in a physical copy by sliding it under the door to my office. Or, I mean, I plan on being here on campus tomorrow. So maybe you can find me in my office or something like that. Anyways, so what we did in class on Friday, aside from the quiz, is we started chapter 2, which was mostly focusing on solving linear equations. And so this is something you probably learned how to do in an old algebra class or something like that. But we were performing elimination. And so we went through a couple of examples. What's important moving onwards is this idea. So first we have this fact, right? If we have a system of linear equations like this 2D problem or this 3D problem, there's only three possibilities in terms of what form the solution or solution set can be. So there's either no solution, which is kind of like when we have two lines that are parallel with one another. So there's no intersection, thus meaning there's no solution. You can have infinitely many solutions, which is when you have two lines that are on top of one another, which I don't really know how to depict. Maybe, I don't know. It's like you have two lines on top of one another. So it's really saying the two equations represent the same line. So you have infinitely many points that satisfy the equation. And then you can have the possibility of having a unique solution, which is when you can have two lines and then maybe there's one point of intersection between them. So those are the three scenarios. We saw a picture of a unique solution represented here. I had two lines and there's just one point of intersection, and these two lines were given by these two equations. So if you want to solve both of them simultaneously, we ended up finding that x is equal to 1 and y is equal to 2 works. And then we went through some other examples as well. Right, so we solved this system of linear equations represented by matrix multiplication and found that there were infinitely many solutions because we ended up getting the equation. The second equation ended up devolving to y is equal to 9 over 4 minus 5 over 4x, which is the equation of a line, which thus has infinitely many points. So for every real number x, you get a real number y, which then gives you a real number z, which gives you a solution. And so as x varies continuously, you go through every single possible point on that line, which gives you infinitely many points. Then we saw another example where we had no solutions. What no solutions usually means is you perform some sort of row reduction operation or some sort of elimination. And in doing so, you get something of the form of like 0 is equal to some non-zero number, which is impossible, which means that you have no solutions. Section 2.2 is largely the same thing. We're not really introducing any new ideas. I introduced this idea of elimination, which is what we were really doing in section 2.1. Then we also talked about what it means for a system to be upper triangular. And so that's pretty much saying that going from one row to the next, you're losing a variable. So you end up getting the form of like a triangle. We'll say more about that in terms of matrix notation later. And then we also were able to solve the system of linear equations by using back substitution. So after reducing this system to this system, you get 10y is equal to minus 10. Divide 10 by both sides to get y is equal to minus 1. Once you know y is equal to minus 1, you can plug it in to the first equation to get 2x plus 3 is equal to 7, which tells you that x is equal to 2. And so this idea of substituting in y is equal to minus 1 into the equation above is known as back substitution. And so I think we went through one more example. Yeah, that's right. One more example where we solve the following system of linear equations and we end up getting a unique solution via back substitution. And now we're just going to continue onwards. So for this next example, I want you to use the elimination method to solve the following set of linear equations. So we have 3x minus 2y is equal to 12, and then we have 6x minus 4y is equal to 4. This is like a smaller system of linear equations, but you can kind of see there aren't going to be any solutions here. And maybe you're asking how. Well, you can see to go from 3 to 6, you multiply by 2. To go from -2 to -4, you multiply by 2. But we're going from 12 to 4. So if we do like a -2 times row 1 and then add that to row 2, like this will go away, this will go away. But this is not going to go away. So you get like 0 is equal to something. Let's verify that. Let's take this system of linear equations. This is row 1. This is row 2. And so what we'll do is we'll take row 2 and then we're going to take it. So we're editing it. So like this equality just means we're adjusting row 2. So that way it's going to be whatever row 2 was originally. And now it's going to be -2 times row 1. The reason why I'm choosing -2 is I really just want to get rid of this 6 here. So to get rid of this 6, you can take -2 times 3 and then add it to get rid of the 6 here. So row 1 stays the exact same. But what ends up happening to row 2 is you're going to get 0. Right, you have -2 times 3 plus 6 is 0. -2 times -2 is 4. You add that to -4, that's 0. And then you're taking -2 times 12, which is -24, and then adding 4. So that's going to give you a -20. And 0 is not equal to -20, right? Maybe I should write it like this. So there's no solution. It mirrors what we saw in Friday's class with the no solution. We get 0 is equal to something that's not equal to 0. Which is a problem, which is a big problem. So there's no solutions to the system of linear equations. And then we have one more example before going on to a 3x3 system. And we've seen a unique solution. We've seen a no solution. So the next one is probably going to be infinitely many solutions. And so it's the same system, or pretty much the same system, except I fixed the previous problem. So that way the constant we have here is now twice as much as the first number. So that way when we do -2 times row 1 and we add it to row 2, it's going to get rid of everything. So you get like 0 is equal to 0. And then that's going to end up leading to infinitely many solutions. So pretty much the exact same step as we did before, except the numbers are a little bit different. So we're going to take row 2. It's going to be row 2 -2 times row 1. And so the first row stays the same. You have -2 times 3x plus 6x is 0. -2 times -2 plus 4, or -4 is going to be 0. Then -2 times 3 is -6 plus 6 is equal to 0. Right, so you end up getting the equation 0 is equal to 0. And so because we have this 0 is equal to 0 here, we're kind of stuck in the sense that we aren't really capable of doing like a back substitution or anything like that. We're kind of just stuck with this equation that we have here. And this is the equation of a line, which is going to describe the various solutions, right? So you can take this equation. This is the same thing as having, say, like 2y is equal to 3x minus 3. And then you can divide by 2 to get y is equal to 3 over 2x minus 3 over 2. So that means you have infinitely many solutions, right? The solutions to this equation are defined by a line. A line has infinitely many points. So you have infinitely many solutions. And so we'll see in the future that in this scenario, we have that y is a free variable in the sense that we weren't able to, like we can write it in terms of x. It's not independent of x, it relies on x. Okay, so those are two quick examples. Next, we'll do a 3x3 example. And usually in this class, I don't, unless there's like a trick to the problem, I usually don't go bigger than 3x3 just because it takes so long. Like the more rows and columns you add to the system, the longer it takes, obviously. So, okay. Yeah, so this is the system that we have. I don't think, is there anything worth reading from this? Yeah, the elimination method can work for systems with more than 2 rows and columns. Who'd have thought? Okay, so the example is we use the elimination method to solve the following linear system. And so the idea is we want to take this system of linear equations and we want to reduce it to this like upper triangular form, which pretty much means that after we perform our elimination slash reduction, the final row here should just have one variable. The second row should have two variables, and then the first row should have three variables, which then will allow us to use back substitution to solve the system of linear equations. So I'm going to first focus, there's kind of a process in going about this, which is called the Gaussian uh, like reduction process, Gaussian like row reduction or whatever, which I'll talk about later on in this class, but we'll be doing it in terms of matrices instead of writing it out in this way. That's really the process we're following. So the first thing we want to do is we're going to leave the first row unchanged. And the goal is we want to get rid of everything that's beneath this x, right? We want to get rid of this 2x and we want to get rid of this x. So to get rid of this 2x, we can do the following. So we can take row 2 and adjust it. So that way it's going to be row 2 minus 2 times row 1. So that way when you do minus 2 times x and then add it to this 2x, it's going to go away. So this is going to be x plus 2y minus z is equal to 7. And then you have minus 2 times x plus 2x is going to give you a 0. Minus 2 times 2y minus y will give you a minus 5y. You have minus 2 times z will give you a 2z plus 3z will give you a 5z. Then minus 2 times 7 will give you minus 14 plus minus 6 will give you minus 20. So the point is we remove the x from the second equation to make things easier to solve for us in the future. And then we want to do the exact same thing. So again, what I was saying in this upper triangular form, there should only be two variables in the second row, which is where we're at now. And then in the third row, there should be one variable. And let's just say we're going to make it z. So we're going to get rid of this x here. To get rid of this x, we can take row 3 and subtract from it row 1. So we're going to pretty much do the same thing over again. So we're going to take this row 3 and we're going to adjust row 3 and make it so it's equal to the previous row 3 minus row 1. And so this means we're taking x and subtracting by x will give us 0. We're taking this minus 2y and subtracting by 2y, which will give us a minus 4y. And then we have this minus 2z minus z, or minus z really is going to be plus z. So this will give you a minus z. And then you have 6 minus 7 is equal to minus 1. Okay. So we're getting closer. The only thing we need to do now to put this in upper triangular form, again, upper triangular form, the reason why it's called upper triangular form is I should be able to kind of draw the hypotenuse of a triangle and it kind of captures the variables we care about. Except the problem is we have this minus 4y. That was kind of like going through the thing that we cared about, right? And so all that's left is we just need to get rid of this minus 4y. And in order to get rid of this minus 4y, our eyes should be on row 2, right? If we do anything with row 1, it just means we're going to be adding x back into the fold, and we don't want that. We just want to get rid of this y, and so we can rely on this minus 5y in some capacity, right? So we're going to perform another row reduction or like another elimination. So the first row stays the same. This is equal to 7. The second row stays the same. This is minus 20. And then we want to do something to get rid of this minus 4. right? And so how to get rid of this -4 is you want to multiply this -5 to something such that when you add it to -4, it ends up being equal to 0. That's just going to be -4/5. If you multiply by -4/5, I feel like I should illustrate this. So if you multiply by -4/5, right, the minus signs cancel out with one another, the fives cancel out with one another, and so you're just going to be left with 4. Oops. You just get left with 4, which you then add this -4y, so the things cancel out with one another. So we're going to take the row 3, and we're going to adjust it so it's the previous row 3, and then it's going to be -4/5 times row 2. Right, so again, in multiplying by -4/5, this is going to become a +4, which you then add to the 4y, so it's going to give you a 0. Then it's also not so bad in the sense that when you multiply this by -4/5, this will give you a -4, which you then add to -c, which will give you a -5c. So after performing this, you get -5z. And then this is going to be equal to -4/5 times 20, which ends up giving you a 15 when you add it to the -1, right? Because if you do -20 times -4/5, you get 4, and then you multiply by the 4, which gives you 16, and then you add that to -1 to get 15. Okay, so now it's in an upper triangular form. And why do we want it in upper triangular form? Well, now we can solve for all of the variables in a way that really isn't too strenuous, right? So now if you start from the bottom and then go all the way up, right, we can solve for z by dividing both sides by -5. So in dividing both sides by -5, we get z is equal to -3. So we know what z is. And now we go to the next row. So the next row, we have -5y plus 5z is equal to -20. But now we know what -5z is equal to. And so now we can quickly solve for y, right? So this is the same thing. Maybe this is a bad way of doing it. There's not going to be that much space. So this is like -5y. 5 times z is really equal to -15 is equal to -20. So you add the 15 over to get -5. So -5y is equal to -5, which is going to tell you that y is equal to 1. And now we go all the way back up. We know what y is. Y is equal to 1. We know what z is. Z is equal to -3. And so this is really equal to 2 plus 5. So you have x plus 5 is equal to 7. You subtract both sides by 5, and you find that x is equal to 2. So once you have it in upper triangular form, finding the solution really isn't that bad. Right, so we end up finding a unique solution. And this unique solution is given by x is equal to 2, y is equal to 1, and then z is equal to -3. Right, so again, this part, y was equal to 1, so this part was equal to 2, and then z was equal to -3. So that's where, I don't know, I feel like people probably understand. I don't have to explain it, but so this is like really 2 plus 3 is 5, subtract x is equal to 2. Right, so that's the general process we're going to be following throughout this semester. You're going to see this over and over again, where we start off with maybe like a 3x3 system of linear equations or like a 3x3 matrix. It's the same thing at the end of the day. Then you want to perform some elimination, so that way you make it so as you're moving down the equations, you're losing variables. And ideally, the last row should only have one variable, and then you just use back substitution. So we'll see plenty of more examples, and we'll see how this process can be used to find inverse matrices, which we talked a little bit about last week. So that's the end of section 2.2 and last week's notes. So we'll move on. So you can find these notes online, and I'll be posting the solutions to section 1.3 to 2.2 on Canvas after I'm done recording this video. And so we're going to continue talking about elimination. Again, that's the big idea of linear algebra, is solving linear equations or systems of linear equations. Except now we're going to be performing elimination via matrices, which will have advantages in the future. At the very least, it's less writing, like you don't have to write the variables out, which is nice. And so how do we go from elimination in the previous sections to elimination via matrices? So the first observation is we know how to express systems of linear equations via matrix multiplication, right? So we recall that an n by n matrix can be multiplied by a vector via two equivalent methods. So you can multiply this matrix, 2 by 2 matrix, with this vector via the dot product. So it's like 2 times x1, and then you do minus x2. So that's like the new first row of your new matrix. And then similarly, the second entry is the following dot product, which is x plus 2x2. So that's one way. You can think about it in terms of dot products. You can also think about it in terms of linear combinations where the weights are given by the entries of the column vector. So this matrix multiplication can also be written as x1 times this column plus x2 times this column. And so last week's class, we looked at a few algebraic properties held by matrix multiplication. One property we found was that AB, if you do A times B, it's not always equal to B times A. And it turns out that there are other algebraic properties that are going to fail as well, which is illustrated in the next example. So in this example, it tells us that if we have A times B is equal to, we can have A times B is equal to A times C, despite the fact that B and C aren't equal to one another. Again, this would be nice. Like, this is not a good property, right? You might be thinking, like, even though these things aren't equal, these things are equal. That must be good or something. But it really isn't. Right? Like, if we have these two things are equal to one another, it'd be nice if we can, like, I'm doing finger quotes right now, but it's like, it'd be nice if we can divide by A to determine that B is equal to C. But that's not going to be the case. So if I were to multiply these matrices, it almost feels like a non sequitur. Because I was talking about elimination and now I'm doing like matrix multiplication, but I don't know. It's all part of the plan. So this is A is this matrix here, and then B is 4, 12, 3, 6. Right. And then you do the same thing with A and C. So you do A times C. A stays the same. And then C is 2, 7, 5, 11. So you just multiply these matrices, right? So the first entry is the first entry of the matrix product is the dot product of the first row with the first column. So it's going to be 4 times 1 plus 3 times 1 is 7. I'm not going to explain all the numbers I get, but the 1, 2 entry is the first row dotted with the second column. So it's going to be 12 plus 6, which is 18. And then you should expect, all we're doing is like taking this first row and multiplying it by 3. So after performing the matrix product, it should just be the row we have here, except multiplied by 3. But if you actually check and make sure this is true, right, you do 3 times 4 plus 3 times 3 is equal to 21. And then the 2, 2 entry is the dot product of the second row with the second column. So it's 36 plus 18 is 54, which is what we expected. So that's the product. And we should find that when we take the product of A and C, it should be the exact same thing. So this would be 2 plus 7, or 2 plus 5 is 7. 7 plus 11 is equal to 18. Do 3 times 2 is 6. Plus 15 is 21. And then you have 21 plus 33. It's going to be 54. So you can see the two are equal to one another. The two matrices are the exact same, despite the fact that we have that B and C aren't equal to one another. And so this property that we like isn't always going to end up holding true, where if the product of two things are equal, it must mean that if you divide, you can determine the scalars are the same or something like that. It doesn't end up holding true. You could see, we haven't talked a lot about inverse matrices. We've done a little discussion as like a preview, but if we do have like A times B is equal to A times C, eventually we'll talk about matrix inverses and how it works with respect to multiplication. But the idea with the matrix inverse is if A is an invertible matrix, you can multiply both sides by the inverse. And the effect this has is if you do A times its inverse, they cancel out with one another, which then tells you that B is equal to C. So what we'll see, or what I've just shown, is if A is invertible, then it means that we're going to have B is equal to C. So it must mean A is not invertible. And if you look at A, it's not invertible because this is like the second row is just a scalar multiple of the first row. If this isn't making sense to you, that's not a problem. I haven't really gone deep into this stuff yet. We'll say a lot more in the future. But I have it written down here, right? We'll find that B is equal to C when A times B is equal to A times C, exactly when we have that A is invertible. Or it's not exactly when, right? If A is equal to the zero matrix, it's going to hold true too, but that's not invertible. Anyways, so we'll move on. So the most important matrix in this class is the identity matrix. We're going to use this all the time. What's nice about the identity matrix is that if you take any matrix and you multiply it by the identity matrix, you just get the same matrix over again. So the identity matrix is denoted by I subscript n. It's an n by n squared matrix. So this is denoting the size of the identity. And how you define the identity matrix is it's going to be zero everywhere except along the diagonal, in which case it's going to have ones. So you have ones on the diagonal and then zeros everywhere else. And so the important aspect of the identity matrix is if you do A times the identity, you get A back. Or if you do the identity times A, you get A back. And so if you're doing the 2 by 2 identity, it would look like this. You have ones down the diagonal, zeros off the diagonal. And then the 3 by 3 identity, ones down the diagonal, zeros everywhere else. And just to verify that multiplication doesn't change anything when you are performing multiplication with the identity, here's just one quick example down here. Right, so the big idea is the first row of the matrix product here is it's going to be given by 1 times the first row and then 0 multiplied by everything else. So you're really just capturing the first row of A when you're performing this multiplication. So it's like 1 times A plus 0 gives you A. Then you do the 1, 2 entry is the dot product of this row with the second column. So that's just going to give you B. And then this is going to be the 1, 3 entry is the first row dotted with the third column, which is just going to be C plus 0. And you can see we just picked off the first row. And it's going to be the same idea for the second row, right? So the 2, 1 entry is the second row dotted with the first column. That's just picking off D. Similarly, the next one will be E, and then F, and then the last row, the 3, 1 entry, third row dotted with the first column. You only hit the G, and then you have H, and then you have I. Right, so when you perform the product, you end up just getting the same matrix back over again. So the identity, it's going to show up throughout this class. It's usually what you're working towards in terms of your matrix row reductions, as we'll see in the future. We'll have a lot more to say about it in the future. Just know that it preserves your matrix through multiplication. That's the important part right now. And so now we're kind of getting back on the thread, right? I was talking about elimination and how you can perform elimination via row reduction, or not row reduction, via matrices. And so now we're going to introduce this idea of an elimination matrix. So an elimination matrix is a particular sort of matrix, which is effectively just taking an identity matrix and then just adding one non-zero entry. So the elementary matrix or elimination matrix, they denote the same thing, denoted by E sub ij, is the identity matrix with an extra non-zero entry given by minus L, so like some number in the ij position. Why am I writing it as minus L? What this elimination matrix does is when you perform multiplication by the elimination matrix, it has the effect of subtracting a multiple L of row J from row L or row I, right? So it's kind of like what we were doing. This is a different PDF. This is like what we were just doing, right? So you can represent these kinds of calculations via matrix multiplication by an elimination matrix, which I'll illustrate here shortly. Right, and so the ij here denotes the non-zero entry that you have outside of the ones along the diagonal, right? So this is an example of an elimination matrix, right? So again, it's the identity matrix, except we have a non-zero entry in the 3-1 entry. It's given by this -4. So how does this actually end up working? Oh, yeah. So, I mean, I write it down here, actually. I was going to demonstrate the example, but it's written. So if you were to multiply matrix A by this matrix E, 3, 1, it has the effect of subtracting the third row of A by 4 times the first row of A, right? So subtracting 4 comes from the fact that we have a -4. And then the third row of A by the first row comes from the fact that we have this 3, 1 here. Right. So let's go through a concrete example. So the next question it asks, what does the following matrix multiplication achieve? And so we can see here, we have some elimination matrix. This would be some like E of 2, 1. And so what multiplication should have the effect of doing here is it should be taking row 2 and then subtracting from it 2 times row 1. Because we have like this -2 and like the 2, 1 entry here. Let's actually verify by performing this multiplication. So if you perform this multiplication, the first row is just the first row of the identity. So when you perform multiplication, it just preserves whatever the original first row was. And then what's new is going to be the second row. So to get the second row, you do the dot product of this row with these 3 columns to get the 3 entries. So now we're going to have -2 times 1. So that gives you a -2 plus 1 times 2 will give you a 0. And then you have -2 times 2 will give you a -4. And that's going to then be plus 1 times -1, which will give you a -5. And then for the last entry in the second row, you -2 times -1 will give you 2, plus 1 times 3 will give you 5. So you can see how this -2 just has the effect of multiplying the first row by -2, and then you're adding it to the second row, which then gives you what you have here. So it's kind of like doing the elimination we were doing before, except now it's written in this this matrix multiplication form. And then the last row, nothing changes, right? So the last row is going to be the dot product of the vector 0, 0, 1 with this column, and this column. So it just captures the last row. So you can verify that, or you can just use the thinking I'm using now to see this is like 1, -2, -2. Right, so that's what ends up happening. It had the effect of getting rid of the 0 that we had in the second row. And if I really wanted to, if I wrote this out, instead of matrix notation, if I were to instead use these rows like we were doing before, like a system of linear equations, this matrix here corresponds to the following system of linear equations where you have x plus 2y minus z. That's this part. And you have 2 minus 2x minus y plus 3z. And then the last row, you have x minus 2y minus 2z. And so if we were instead to think in terms like, let's get rid of this 2x here, like how we wrote this before is we did row 2. It's equivalent to row 2 minus 2 times row 1. Again, you wouldn't change anything about row 1. Row 2, you would be doing 2 minus 2 times x. So that would give you a 0. You would be doing minus y minus 2 times y, which would give you a minus 5y. And then you would be doing 3 minus 2 times minus 2z, and then you add it, which would give you plus 5z. And then this would be x minus 2y minus 2z. So if you read off the coefficients to x, y, and z here, you see it's exactly the same as the matrix that we just found via the multiplication. Right, so we're doing the exact same thing. We're just writing it more concisely via this matrix multiplication instead of this more laborious way of writing it in terms of like x, y, z's, arrows, r1, r2, r3, so on and so forth. It's the same thing at the end of the day, so whichever way you prefer. There are advantages to doing it in this way, but I do think it is a little bit harder to think about, perhaps. I don't know. I feel like this is actually the easier way of thinking about it once you get used to it. It's just a matter of knowing like this -2 kind of corresponds to this -2 right here. So we'll see more examples. Actually, we're going to solve this, or at least we're going to put this in linear or in upper triangular form in the next example. But I want to say a little bit more now. So this matrix multiplication, what we just saw, can be used to keep track of the elimination steps used to solve a system of linear equations. Before going through the next example, we have the following definition. So this is redefining what it means for a matrix or for a system of linear equations to be upper triangular, except in terms of matrix notation. So a square matrix A, where all entries below the main diagonal are 0, is called upper triangular. So in other words, what this is saying is that the ijth entry of our matrix is equal to 0 whenever we have the row index I is greater than the column index j. I'll show you what it means here shortly. It will make more sense probably after I go through the next example. So we're taking the next, so we want to take this matrix A. It's the same matrix we were looking at in the previous example, and it wants us to put it in upper triangular form through matrix multiplication. And so we've already gone through the first step, right? This was the step that we did, the first step we did on the previous problem. Instead of copying and pasting, I'm just going to read. So we did the following on the previous page. This is 1, 0, 0. So if we want to get rid of this 2 using this 1, it means we're going to be doing -2 times row 1 and then adding it to row 2, which amounts to having this like -2 here. So this was E2, 1. And again, you should be thinking, if I want to get rid of this 2, the 2 is the 2, 1 entry. So that's why you have like this 2, 1 here. And then like we need to multiply this by -2 and then add it to 2 to get rid of it, which is where this -2 comes from. And then again, with elimination matrices, everything is, it's just the identity matrix except that one particular entry. And then we multiplied it by A. So this is 1, 2, -1, 2, -1, 3, 1, -2, -2. And upon performing this multiplication, this was 1, 2, -1, 0, -5, 5. And then we had, the last row stays the same. And so if we want to put it in upper triangular form, what that means is the entries of the matrix need to be 0 whenever the row index is greater than the column index. So 2, 1 should be 0, and it is 0 now. But we also have 3, 1 entry and the 3, 2 entry. We need to make it so this and this are equal to 0 as well. Right, and so next we want to get rid of this 1 here. And so if we want to get rid of the 1 and the 3, 1 entry, that means we're going to be doing the elimination matrix corresponding to the 3, 1 entry. And so again, it's just going to be the identity matrix, except at the 3, 1 entry. And if we want to get rid of this 1 here, what we need to do is we need to multiply row 1 by -1 and then add it to row 3 to get rid of the 1 that we have. So we're just going to make it so we have -1. And then we multiply this matrix by the matrix we have here. Right, so this is going to be 1, 2, -1, 0, -5, 5. The first 2 rows stay the exact same. The only thing we're changing is the last row. And so if we do -1, oh, wait, what am I doing? We're just keeping the, now we multiply. Sorry, I was like thinking about the matrix multiplication already. Right, so we multiply this elimination matrix by the matrix we derived earlier. So again, the first 2 rows stay the exact same. The only thing that's changing is the third row. And then the third row, we do -1 times 1 and then +1. So it's the dot product of this row with this column, which will give you 0. Here you have -1 times 2 is -2, and then 1 times -2. So that'll give you a -4. And then lastly, the 3, 3 entry was the third row, third column. It's going to be 1, and then -2 will give you a -1. Let me shrink this. I kind of wrote it pretty large. All right, so we're 1 away now, right? The 2, 1 and the 3, 1 entries are now equal to 0. To put it in upper triangular form, we just need to get rid of this -4. So this is in the 3, 2 entry. So that means we're going to want to use the 3, 2 elimination matrix. And so I'm going to copy and paste. We're going to multiply this matrix by something. By something, I mean the elimination matrix. Right. And so the elimination matrix, again, is just the identity, except at the 3-2 entry. And in terms of what entry this is going to be, we want to get rid of this -4 that we have. And we can't use row 1. If we use row 1, like multiply something by row 1 and then add it to row 3, it means we're going to get something non-zero in the 3-1 entry again, which would be undoing the work that we were doing before. So we need to use, well, I mean, it's kind of written here, right? We need to use the second row, right? So these numbers tell you which rows you're working with. It means you're taking row 3 and subtracting by something multiplied by row 2. And so we have to work with this. I mean, it's similar to the example we saw before, right? We want to take this -5, and then we want to use it to get rid of this -4 that we have. And just like we saw in the previous example, or not the previous, but an example we worked on earlier today, you can multiply this by -4/5 to get a 4, and then you add it to this -4. So this is going to be -4/5. Again, that's to make it so when you multiply this -4/5 by -5, you get +4. And then when you add that to the -4, you get 0. So now when you perform the matrix multiplication, only the third row changes. So the first 2 rows stay the exact same. And then this is still going to be 0. And so now when you do to get the 3-2 entry, you do the dot product of the third row with the second column. So it's going to be 0. And then you're going to have -4/5 times -5 will give you 4. And then that's going to be plus -4, which gives you 0. So you have 4 minus 4 is 0. And then for the last one, the 3-3 entry is the third row dotted with the third column. So you get 0. And then you get -1. And then you get another minus, or you don't get -1, you get a -4. And then you get a -1. So it gives you a -5. Right. So now it's an upper triangular form. Oh, hold on. I don't know why I put the zeros there. Like there should be 2 minus 1. Right. So now this is an upper triangular form. You can kind of think again in terms of, right, like the non-zero entries can be inscribed within this triangle. This is one way of thinking about it, I guess. Right. So this is how you put something in upper triangular form. If I were to write it in terms of a system of linear equations, oh, I mean, actually, these were the exact same entries we had before. I didn't even notice that, to be honest. But yeah, now that it's in upper triangular form, you can now use back substitution to solve for x, y, and z, right? So like the coefficients that we have here are exactly the same as the entries of the matrix. So we did the same problem over again, except in matrix, using matrices instead. And I mean, I don't know. It isn't that much. I don't know. The amount of work is pretty much the exact same, to be honest. But it's just a different way of thinking about it. Eventually, we're going to do pretty much everything in terms of matrices. So this is kind of the interpretation that's going to win out. This is the elimination via matrix multiplication. Okay, I think I have time for one more idea. It's this idea of permutation matrices. These permutation matrices just give you a way of flipping around the rows of your matrix. And it's kind of intuitive in the sense that to get a permutation matrix, you just take your identity matrix and then you flip some of the rows around. And then the corresponding rows are going to be flipped upon multiplication. What do I mean by this? So I'll go through an example. I guess I should probably read off what's written here. So sometimes, like, why do we want to use these permutation matrices? Why would I want to switch the order of things? So sometimes it's necessary to exchange 2 rows in order to produce a triangular matrix. Like you could go through this above process as we did above, except you could get rid of like these variables and then you can perform some sort of permutation. So that way they show up like down here or something. That's something you could do. And so how do you end up switching the order of the rows to produce a triangular matrix? This can be accomplished by interchanging the same rows of the identity matrix and then performing multiplication. So if you take the identity matrix and flip some of the rows around, such matrices are called permutation matrices. Right, so let's start with B. before going with A. I mean, D is the simpler example. I don't know why I wrote it second. So with B, right, we have this matrix 0, 1, 1, 0 multiplied by the matrix B, 1, 1, B, 1, 2, B, 2, 1, B, 2, 2. So like this matrix 0, 1, 1, 0. We can get this matrix by taking the 2 by 2 identity matrix 1, 0 and 0, 1, and then just flipping the two rows that we have. So that way the second row is now the first, and the first row is now the second, right? If we flip row 1 with row 2, we get this matrix here. And the effect this has upon multiplying by this matrix B is if you perform this multiplication, you now, I mean, just think about it, like the first row is now going to be the dot product of this row with these two columns, and you're just picking off the second row here, right? So if you do the dot product of this, you get B21. And then this, the 2, 1 entry, or the 1, 2 entry is the dot product of the first row and the second column, which is going to give you B22. Right, so now the second row becomes the first row. And then if you find the second row, it's going to be the dot product here with these columns, which is going to give you B11 and B12. Right, so we took our matrix B, and then we just flip the rows, right? We just flip the rows, and it has this effect. Right, so that's how you flip rows via matrix multiplication. So now we know how to do elimination, and now we know how to permute things. And then I'll do the larger 3 by 3 example as well. So this example here, this matrix, it's effectively the 3 by 3 identity matrix, except you're taking the first row and you're switching it so that way it's going to show up in the third row instead. There isn't like a great notation, but it's like one way of thinking about it. So this is like the third row of the 3 by 3 identity, right? And then we're now making it so the first row is going to be the third row. And so if you perform matrix multiplication, what we should expect is the second row is going to be fixed, and now the third row is going to be the first, and then the first is going to be the third. That's exactly what ends up happening. So when you perform this matrix multiplication, the first row is going to be this. The second row is going to be fixed. My alarm went off, so that means I'm pretty much done with class, or maybe I'm over time. I don't know. This is B11, B12, B13. Right, so by adjusting the rows of the identity matrix, you get these permutation matrices, which has the effect of switching the rows of your matrices. Okay, so we'll make use of this later on. I think particularly when we do like the LU factorization. So in class on Wednesday, we'll pick up with the final example in section 2.3, which is focusing on multiplication by columns, and then eventually looking at augmented matrices and actually solving a system of linear equations via matrix multiplication. Okay, so if you have any questions about the homework, I mean, I'll be on campus tomorrow. I'll post my office hours for the semester later today, now that the poll has closed. If you have any questions, you can email me. Otherwise, I'll see you on Wednesday.